My name is Balaz Kieth. I'm the founder and contributor of WebRTC, and I'm going to talk about a little bit more dull topic than before or after me. I'm not going to talk about how to make the world a better place or making $1 trillion in the future. I'm going to talk about how real-time communication works, what happens in the behind of the scenes when you are opening the browser and want to talk about somebody, interactive multimedia communication on the other side of the world. And for that, I'm also going to talk about the history a little bit. So just to know what WebRTC is and what is the technical background. So WebRTC is, the long story goes back in the 1990s when in the IITF conferences, a small library called NV is used to use multicast and multicasting video conferences. Then the short story is coming in 2009 when Google Chrome team had an idea. What if we can use a unified application programming interface in order to create in the browsers real-time communications so you don't need to install any applications, you just need to open the browser. And the idea in 2011 was the year when two big players entered into the market. One was Google by acquiring GIPS, the Google IP solutions, and the other is Microsoft, who was acquired Skype. And in 2011, 1st of June, the journey started. They started to aligning WebRTC and IITF standardization in order to build the web that they called web real-time communication. In 2013, Firefox and Chrome started to supporting it, and the champagne was open at 2017 when it was officially designated as a release candidate, and that's where the journey was started, really. And for the future, we know that after we making the application programming interfaces unified in the browser for the RTC, we also can make it for the transport, so that's where the industry is heading to. But the WebRTC, how it works behind the scenes, is three main components and three main stages. So first of all, your device is opening WebRTC, communicating into a signaling service in order to establishing the connection. The establishing connection is called through the ICE or Internet Connectivity Establishment Service, and the media flows through the media service. The majority of the RTC is actually using UDP, or sometimes it's TCP, but that's just a stack. It's not relevant in this way. But I'm going to talk about more how to designing behind the scenes a WebRTC architecture and what was the evolution since 2017, 2015, and how we are being driven to making a better quality, and how it's shaped the architecture. In order to understanding the architecture, we need to understanding the main components and how the WebRTC backend is built. There are three main components: the signaling service, the ICE turn service, and the media service. And there are three types of media services we can talk about. One is the peer-to-peer, which doesn't require any backend in order to relaying the media information. One is the calling MCU, the multi-point control unit, which is having an advantage is that it has everybody is publishing their stream, and you have only receiving one stream. It doesn't matter how many people is on one call, everybody is receiving one stream. And that's important in terms of the bandwidth usage and computation, because if you have 10,000 people listening to one speaker, everybody receiving one stream, and 10,000 people can theoretically publish the stream into the same server. But we are using the so-called SFUs, which is the selective forwarding unit, where you are publishing your media stream, which is you're sending out, to a media service called selective forwarding unit, and that's relaying the media to those who is in the same group to you. We can call it room, we can call it call. It doesn't matter so much. When we are talking about designing a WebRTC architecture, we are having three main aspects. One is scalability, the second is security, and the third is quality. And quality is the main factor which driven this industry, what we know today. But the scalability to talk about, to imagine the problem, is that we are not talking about how many clients, or not just talking about how many clients are joining to the same group, but what is the average number of people going to join in one group. So let me give you an example. If you are using an SFU, which usually most of the company is doing, that if there is 4 people on the room, each of the 4 people needs to consume 3 streams. So altogether, it's 12 streams, 4 outgoing, 12 consuming. And when you are increasing the number of people, the number of streams you are consuming is quasi-quadratic. So it's giving a problem. And that's the first problem you need to know about for scalability. The security is the other aspect, that everybody wants secure connections. The WebRTC stack is built on security in the terms of DTLS and SRTP, which is providing you end-to-end security between the 2 endpoints you are joining to. The problem is that if you are using media service, the other endpoint where the WebRTC connection ends is the media server. So end-to-end security in terms of using media service is not ensured until some else security addition is actually installed into your system. And this is also needs to be considered when we are designing. Also, we need to considering what are the services blast radius, how many rooms or meetings going to be interrupted if one of the server crashes. These are the aspects of the security. But the most important, and generally what is driven the whole architecture to be shaped as of today, is quality. And quality is something very hard to measure, especially because we have quality of services and we have quality of experience. Each of you, when we are seeing somebody on the stream, on the video, you have a quality of experience, and that quality of experience is hard to measure. But we know for quality, from the quality of service point of view, that there are 3 things which is crucial in that: resolution, latency, and reliability. Resolution, because if you are seeing a video in a higher resolution, that's meaning better quality. Reliability, because if it is glitchy, then it's not reliable connection, so it is important that the bandwidth and the resolution not fluctuating. And latency, because in real-time communication, we don't have the luxury to resending any packets which is lost. And moreover, we don't have the luxury to buffer packets. For example, if you are watching a YouTube video, your browser has the luxury of buffering 5-10 seconds, depending on how many it wants to buffer. But in real-time communication, if we would play out a 10 seconds delayed voice or video, meanwhile you are expecting that it should be interactive, it wouldn't. And that latency was the key factor why we changed the original design of the architecture that we had. In the early days of the WebRTC, and when the media services started to installing in the backend, we had one server point, one media service, one signaling service, and they are tied together into one node. And that node was the key. When 1 people from US and 1 people from Asia, for example, try to actually connect to the same group and try to communicate with each other through video, they signaled each other with the TMD signal service, and often it was the media service, so they published their stream and consumed their stream from that media service. Now the problem was that, where do you put that media service? What is going to be the latency? What is going to be the best location? Who will determine the location of the media service where they are communicating through. So if one people in California and then one people in Delhi, what would be the best location? Would it be Beijing? Would it be Tokyo? What would be it? How much would be the latency? Moreover, there was a false assumptions in that, and that was that the internet providers are responsible for making a good quality call for you. But that's not true. Internet providers only responsible for making a connection between the two endpoints, and their responsibility ends there. They don't care what is the latency between the two endpoints, how many packets lost. Well, they do care, but mainly they are optimizing their routes based on costs. And so, for these things, we redesigned the whole system, and the next phase was that we use the phrase of cascading. So whenever people from US and from Asia wanted to communicate with each other, they didn't join into the same media service or signaling service maybe. They joined to the premises of media services, and that provided the best latency. And the WebRTC backend provision company, whatever we are doing it, we are responsible for making the connection between the media services. And that gives us much better latency, gives us much better quality in terms of the video communication. That is actually the main factor since 2021, when in the Cranky Geek it was published, that it's yielding far much better results than before in terms of the quality. And the next phase, what we started discovering with this architecture, which is a problem, is that the signaling service and the media service tie together, and it's really hard to coordinate or orchestrating meetings. So the next architectural revisioning was this. When we decomposed the signaling service from the media service, and the signaling service keep giving an own node, somewhere location is actually not so important because we only using the signaling service to establishing the communication between the media service. The media services are sitting on the premises. You are consuming and producing to the media, to the closest media service, but you are communicating with the messages to the signaling service. And the signaling service is orchestrating the media services in order to making a cascaded connections in the background, and then you will have a better quality. And that's yielded much better results, and ergonomically a little bit better. It's still not clear this is much better or better than the previous one, but this seems to be the way it's going forward with the backend architectures. Now, it was the quality which was drove the architecture as we know for today to the cascaded SFU architecture. What is hard to do is that improve the quality of experience for WebRTC adaptively during the call. So let me give you an example that we can provide the best latency or better latency than before by this cascaded environment, but it's not sure that it will be remaining, or it's not sure that our first choice was the best one. It's not sure that anything during the call, during 2 hours call, remained the same. So we need to adapting it. And as I said in the beginning of my speech, the hard problem with the quality is that you have a quality of experience which is subjective, and we have a quality of service which is a measurement from the WebRTC. Quality of service is that the WebRTC stats, like the latency, like packet loss, like frame loss, like packet loss indications, like so many other things. There are application events when the web applications are signalizing that what's kind of happening, what's the user requesting. And those are the quality of service metrics. And we can convert it to the indicators indicating what is the point of view or the quality of that participant or the room. That can be turned or transformed into a quality of experience. The quality of experience is what the user feedbacks or user ratings doing, and these indicators are, is that the more close to the quality of experience the user actually ratings. And this is what we are going to see today, is that the quality of experience is turned into controllers, and the controllers is tuning the quality of service for the car. So it's an ongoing adaptive cycle when we are tuning the real-time communication experience on the time and making the best quality. And for that, we can need to observe the RTC calls continuously. And for that, we can use many tools. I designed this WebRTC in order to providing open source tools to everyone to make their analysis on the web applications you are using and improving the quality of experience for the users. A bit about the history of WebRTC. The GitHub repository was open 2020, and the version 1 came out 2 years later when it was used by some companies. And the version development, the second version is in development today. And the second version is designed to be part of the architecture, what we using today. So the addition of that, what we discussed, that the signaling service is decomposed from the media service, we can add an observer next to the signaling service and continuously adapting the experience and the quality for the users. And that's it.